My name is Oleg. I work as a developer advocate for the GraalVM team at Oracle Labs at Oracle. Oracle Labs is, of course, the research and development department within Oracle. So that's where people do science, right? They produce academic advancements and push forward the boundary of the knowledge about how to do computer science stuff, including how to build virtual machines. If you, I would actually like, so I would like this session to be very laid back, right? So it brings me joy to have interactions with people. So if you have any questions, please ask them, and I'm sure there is a process how well, I can be interrupted by either the host, or I can monitor the chat as well myself, even though I cannot promise that I will be very responsive there, right? So yeah, all the questions without any delays. If you have a question, or if something is like, if you want to like try, if you want to make me elaborate on something, right? This is like where you want to stop me immediately, because in any case I would answer the question or postpone it until the end of the session. But it would be much better if you actually like leave it out, rather than you will sit on it and then forget about that, right? So let's make it as interactive as possible. This is December of 2020, after all, like a tough year, strange year. If you don't have the questions now, or if you watch the recording for this, you can find me on the internet. I go by @Šelajev almost universally, and I'll be happy to chat about GraalVM or software development or anything really. So let's get started. Before we go to the technical stuff, I want to say that this is a technical presentation, so please do not make any foregoing business decisions based on the contents of this. And also note that GraalVM native image is distributed under the early adopter status, which means that it can significantly change going forward. So with all that, all those requirements out of the way, let's talk about GraalVM. And I know that you've had a few sessions here that mentioned GraalVM, at least I hope so. I caught like a really interesting talk, great talk about Micronaut by Ivan, and he talked about GraalVM a little bit, so you know about that. And I would like to just quickly elaborate about this, just to, I don't know, like to cover the basis, and then we'll talk about how you can use GraalVM for your Java applications. Right, so GraalVM is a high-performance polyglot embeddable virtual machine that supports multiple languages. Right? We support the JVM languages, including Java and Scala and Kotlin and Clojure and I don't know, Ceylon and Groovy, right, and others. And also we have support for JavaScript applications, including Node.js applications and some Python and WebAssembly and Ruby and R. So there is plenty of languages, like a fleet of languages that you can run on GraalVM. And it's absolutely marvelous because all those language implementations share all the advancements of the underlying platform, right? So it builds on the JVM, it builds on the OpenJDK project. So all the enhancements, right, benefit all the languages. And that's how we get really good performance for them. GraalVM includes a state-of-the-art JIT compiler, so your languages the programs get optimized quite well at runtime. So that's the high performance aspect of it. Then there is the polyglot aspect, which is very interesting, even though maybe a little bit less straightforwardly applicable in the day-to-day life. Right? All those languages look the same from the virtual machine point of view. So you can mix and match and build systems where different components are written in different languages. And this whole thing is embeddable. So that means that you can easily put the GraalVM technology into your Java or native applications and benefit from enhancing that with the ability to run, I don't know, some Python, for example, which is very cool. So we're going to talk about the main advantages for Java developers and Java applications. And I'm using term Java here very loosely, right? Anything that works on the JVM will be a Java application. So in a sense, it's a JVM application that is distributed usually as a bunch of jar files, like in the form of the Java bytecode. So don't quote me officially, right? This is not the most precise ways to say that, but after all, if it goes through bytecode, let's pretend that it's a Java application. So what GraalVM can do for you if you are a Java application, right? The most straightforward and the easiest benefit that you can get is that you can run your application with better performance by using the GraalVM's just-in-time compiler. What it means is that GraalVM includes a compatible JDK, but the top-tier optimizing JIT compiler is replaced with the GraalVM compiler, which very often produces better machine code. So when you run your application normally, at some point of time, it will get faster. So this is one way. The second way is that GraalVM includes the ahead-of-time compilation technology called native image, and that can take your application and compile that ahead of time to the machine code and put that into the platform-dependent binary. So it makes a standalone file that you can double-click and run, and it doesn't depend on the JVM, and it has a different performance profile that very much suits the needs of an application in a cloud deployment. And we're going to talk mostly about that part for GraalVM, because for the cloud deployments, if you want to use GraalVM for the cloud, those two are a match made in heaven, right? So, and then the third one is a multilingual virtual machine. You can use your Java application and you can include components written in different languages. So the same way as older Java releases, OpenJDK releases contained NASRun for JavaScript execution, GraalVM can execute modern ECMAScript 2020 compliant JavaScript. It can execute Python and other languages, Ruby, R, and even the LLVM bitcode. So if you want to execute a native application on GraalVM, you can do this. For Java applications, normally you would use it as a component within your Java application. For example, you can write your logic in JavaScript and run it on the proven web stack, for example, based on Netty or something. Thus, merging the ecosystems and leveraging the teams that you have in the company or in the project more efficiently, right? And you can also there are other ways how to do polyglot, which is very exciting, but it deserves probably a separate session altogether, right? So those are the three main use cases for Java developers, how GraalVM can help you with Java applications. How do you get started with all this greatness? It's fairly easy. You download GraalVM, right? It comes in a distribution, so it's a package. You download that package, and it's an archive. You unpack this archive, normally doing this incantation tar minus extract the files, which is the very helpful mnemonic for remembering how to unpack an archive with tar. And then you just put the result on the path. You can export either GraalVM home or Java home, and then put it on the path. And then in the bin directory of GraalVM distribution, you find the normal Java executable. Actually, you find all the normal Java commands that you expect from a GraalVM, from a JDK distribution, because GraalVM contains a JDK distribution, right? And then you can run your application normally. And this is very easy and very straightforward. So let me show you. Let me show you very quick. Let's go here. We are in a cloud machine. Look, this is a decent cloud machine, right? It has some memory. It has some CPU available. I made it a little bit smaller on my screen, so we are actually looking into the middle of the screen. If you have other ideas how to do this, just tell me if it's like the font is too small or anything, right? And I have when I do Java minus version here, you can see that I'm running the GraalVM, Java from a GraalVM distribution, right? It's a Java 11 based build, so it builds on the Java 11. So I have the normal Java 11 things. So if, for example, if I go to the GraalVM home and I go to the bin directory, and then I look what's in there, you can see that there are all the normal Java facilities are there. So you have your Java, you have your Java C to compile your Java source, of course. You have your jar command, you have your JConsole, JImage, JInfo, JLink, if you'd like, JShell, and so on. You also have the other things that are actually GraalVM specific. For example, we have the Node.js binary here that you can run Node.js applications. We have the LLVM bitcode interpreter. We have the JavaScript REPL, and so on. We have Ruby Ruby stuff here. We have the WASM, the WebAssembly interpreter, and all that is inside the GraalVM distribution. Some of that are additional components that are not the part of the base GraalVM distribution, but you can install them into the GraalVM to enhance its capabilities, right? So this is my Java 11 here, right? And I can do normal things with that Java. For example, I can run a Java application normally. So GraalVM has distributions. Two distributions that we're currently offering is Java 8 and Java 11 based. So if you're running one of those, if you're running your applications on one of those, you can use GraalVM out of the box for your applications. And you should. You should, because Java there is probably faster than other Javas that you can use. Right. If we have any sort of the feedback capabilities here, for example, if you're in the Discord channel, I would absolutely enjoy if you could respond with 8 or 11 or whichever version of the JDK you're using normally for your production applications. That'd be cool. Don't have to, but I'll appreciate the feedback there. Right, and we would like to work on, we're actually working on the more modern distributions of GraalVM that are using more modern JDKs as the base JDK there, but they're not available yet, as of yet, right? So that's it. Let's go back, right? So how to get started? We can run our applications. Why would we like to run Java applications on GraalVM is because it can offer you better performance, and performance means money, specifically when we run our application on the cloud, where we actually have to pay for the compute power that we're consuming. So think about this: if you run a large business and you want to build, and this is an example of an on-premise deployment, not in the cloud, but it translates easily to the cloud as well. Imagine a runtime gives you 20% better performance, right? 20% better performance. And your plan is that you need to build 5 data centers, actual buildings with the servers and everything to satisfy the needs for your business needs for your application, right? 20% means that you have one less data center to build. That means that you can save quite a bit of money, which is very simple. And also it's good for the environment, most probably. People are telling that better performance is great for environment. One company that is using the GraalVM technology for their production services is Twitter. Twitter uses GraalVM compiler. As far as I know, they're not using our builds, but they're using the compiler and put that into their builds to run their Scala microservices and do that with quite a success, right? So the microservices run faster. They save on the CPU. They also see less garbage collection. They also see, so the throughput is better there. And they save on the resources, and it saves them quite a bit of money. Oracle Cloud infrastructure, right? The Oracle Cloud migrated some telemetry services. I think it was last year, which feels like actually like a forever ago. But it was just last year. Oh, sorry, migrated some telemetry services to GraalVM. They saw improvement in the peak performance. They saw reduced garbage collection time. They saw no problems while migrating. So it's good, right? You run your application. The general rule of thumb is that GraalVM gives you better performance. So for example, we know that because we run a ton of benchmarks, right? Like we always run a ton of benchmarks. Otherwise, how can you be like a high performance runtime if you don't actually measure? And we know that it shows great results. One of the benchmark suites that I would thoroughly recommend is the Renaissance benchmark suite. Why I like this a lot? Because it consists of the benchmarks from other projects, the real life projects that are specifically selected for certain criteria. Some of the workloads there are memory intensive, some of them are CPU intensive, some of them use like the immutable data structures, some of them use the Stream API, for example. You can see there are some reactive Scrabble and some project reactors, right? Some of them use a lot of data. So for example, I think there was a Neo4j Analytics, which is a database database-based workload, Neo4j is, of course, the graph database there. There is some Akka, there is some Dotty, right? So modern libraries and frameworks and modern technology that you're probably using in your application. And it shows great results on that. Of course, we run all the other normal ones as well, the capo and spec benchmarks and everything. But if they're a little bit older, right, then maybe you don't actually write your code in a way that those benchmarks have been written like, what, I don't know, 15 years ago. So there is no substitution for actually running your code on it, but this is a very good results here, right? And what we also know is that there is a constant improvement happening in GraalVM. So last year we released, we have 4 releases a year, right? Last release of last year was GraalVM 19.3. And compared to the last release of this year, so 1 year improvement, saw approximately 6% improvement across all the workloads. Some of them, though, like individual ones, of course, got much more. Some of them didn't change very much. But this is like, you have to realize that this is compared to the best in class already, right? So the baseline is really good here, and it got much better as well. 6% over a few years gives you quite a bit. So there is no reason not to run your applications on GraalVM. Specifically, if you use some other JVM languages other than Java, they typically produce a little bit different bytecode patterns, and then on those, the GraalVM compiler has even better performance results. Like the performance boost is typically a little bit better than running applications that are compiled from Java code. Because usually C2, which is the default compiler in OpenGTK, is a little bit better at compiling the bytecode that comes from Java applications rather than, say, for example, Scala applications. Right. So yeah, you should use GraalVM. That's easy. Just run your applications. Right. However, cloud is a little bit different. And I hear very often is that, oh, nobody needs the compiler anymore, right? Nobody runs those long-running processes. Everything is run in the cloud, and the cloud cares. Like the cloud use case is very different, right? In the cloud, we care about the different performance characteristics because our deployment model is different, right? We take the application and we try to package it into the smallest constrained environment that we can possibly put it into, so it still satisfies our business requirements, our SLA, for example. So we pack everything into Docker containers or like any other containers, and we let actually someone's infrastructure manage it all, right? So it's either the cloud platform or we run the Kubernetes cluster. But usually we don't deploy our applications manually, and something else just manages that and autoscales that based on the traffic requirements. So you get that nice curve of the billing that follows your actual traffic and actual the business needs for the compute resources that you use, rather than you have the pre-provisioned concurrency and you pay for that all the time. So that is the great promise of the cloud. And that is where typically long-running processes don't do that well. Because if you have a long-running process, you need to give it more resources for the JIT compilation. You need to probably give it more resources to enable more sophisticated garbage collection. And there is a conflict of interest between packing into the smallest and actually giving it enough resources to make it work normally, right? So if you think about performance, there are different things that people say, oh, this is good performance versus bad performance, right? Normally, the JVMs and Java applications are geared toward the peak throughput and the best latencies they can get. And this is very normal. If you deploy it into the environments with a ton of resources, you don't actually count every megabyte. You just say like, oh, here's a gigabyte of RAM for you. Just give me good peak throughput. That's one thing. But some requirements, some situations, some use cases require you to have better startup speed. For example, if you want your services to be auto-scalable, you cannot wait like a couple of minutes before they get warmed up and everything, right? You want them to start up and be doing the business service as soon as possible. You also want the memory footprint to be smaller, actually. And very often in the cloud specifically, memory footprint is the performance characteristic that you optimize for, because that's what you're paying for, right? If you use any serverless platform, you most likely are paying for memory the most, and the rest of the resources are just scaling with the amount of memory you consume. Small packaging is also important. You want your applications to be neatly packaged so you can throw them in the cloud as efficiently as possible, because nobody knows how they are actually getting deployed, right? So if you think about the cloud use case, there's this clear line where for some services you want the startup, memory footprint, and packaging, and for some services you care more about the peak throughput and the latencies. This is very normal. So luckily, those two use cases are very naturally covered very well by the different mode of operation. If you want peak throughput or maximum latency, you are using the JET, right? The JET is probably the best option you have if you want to achieve the best throughput, right? And if you want the other ones, if you want startup speed until you hit the best performance, you probably want to have an ahead of time compiled application, right? Because then you don't need to actually compile it at runtime using your expensive resources. And the compilation, of course, needs to take some memory. So by disabling the JET, not using the JET, you can save on the memory footprint as well. So those two use cases, and they're very nicely covered by GraalVM, right? So you can take your Java application, you can run it with the JET, normally with the Java command, right? And it will run in the context of the OpenJDK, or in case of GraalVM Enterprise, Oracle JDK binaries, Oracle JDK. It will be based on OpenJDK or on some JDK, right? Or you can build the ahead of time compiled binary from the application by using native image utility and feeding your classes to that. And then you just run that standalone application as a standalone application. Doesn't depend on the JVM. Doesn't run with the OpenJDK. Doesn't just standalone. Double click and run, or set your entry point towards that and make it run. What happens there is that when you feed your application to the native image, a very important thing happens. All the Java code in your application gets analyzed, initialized, precompiled, and outputted to the binary, right? So that includes your application classes, the dependencies that you are using, for example, your framework, the JDK standard library classes like the Java util array list, or some stream classes, or I don't know, local date time or something else, and also the components of the virtual machine that you want your final executable actually have access to. For example, you want the GC, right? You want garbage collection because your application will still run as if memory is infinite. So something has to manage memory for it. So there is an implementation of the GC that comes in there. Those components are coming from the Substrate VM project, which is the part of the GraalVM overall project, right? All that is written in Java, right? So all that on the left, the gray rectangles here, is the Java code. So it can be run, it can be initialized, it can be looked upon, it can be statically analyzed, snapshotted, both heap and the ahead of time compiled code, and it gets into the executable. And this gives you excellent results. But there is also a trade-off. The main trade-off is that this analysis and this compilation process happens under the closed world assumption. That means that while you statically analyze this application, while you run this native image utility, which is a part of the GraalVM distribution, it needs to see all the bytecode that will ever be executed in your application, right? So that means the very straightforward trade-off for this is that there will be no loading new classes at the actual runtime of this native image. You can load new classes, and you can use reflection, you can use all the Java features while you're building the native image, because that is the normal Java process. But after you actually output this executable, it doesn't include anything that knows how to deal with the bytecode. There is no JIT compilation, so you cannot load new classes in there, right? That is a downside, of course, but the upside from that is that it allows us to use very aggressive speculative. They are not speculative anymore because we do see the bytecode. Some aggressive ahead of time compilation optimizations. For example, if we know that some things are never null, because we know that everything that calls it never passes null, we can eliminate some null checks. right? Or if we know that the class hierarchy, like there is a single implementation of the interface, for example, and we know that the method call will always go into that implementation. And since there are no new classes, the class hierarchy cannot change. We know that we can maybe just link directly to that method call rather than going through the invoke virtuals and invoke special for the interfaces and everything. It also allows us to eliminate the unused classes, methods, and fields very efficiently, right? The native image analysis doesn't compile, doesn't include in the executable anything that is not used, which allows us to keep the output quite small and also has other benefits, right? So that also means this analysis is static. So that means the dynamic parts of the language require some configuration. So if you're using reflection or GNI or proxies or use class loader resources, you need to provide a configuration because those things you use actually through strings. So you don't, like, the static analysis cannot know what resources you are trying to access, right? So you need to include a JSON file that it's currently in the format of a JSON file that says, please include that my resource. Please include my JavaScript file because I want to serve it from my web service. Please include this image file because I want to serve it as a fav icon, right? Please create the proxies for those classes because something, right? The best way to use this, to create this configuration is to use a Java agent. So you don't have to actually write it by hand. There are a number of frameworks that help you with that, but there is also a Java agent that can just, you run your application normally, you use it, and it outputs the configuration for you. There's nothing simpler, right? So the closed wall assumption is where those trade-offs and the need for configuration comes off. It gives you, though, really, really good results. So, for example, this is the graphs for running two small applications. One is it's actually the same application, but one is using the JIT, the other is using the ahead of time compiled mode. And you can see that in the JIT mode, it uses quite a bit of CPU in the beginning when the JVM is starting, and somewhere after where the requests start to come in. This application, the test here is very simple. It serves 3 requests 1 second each at 1, 2, 3 seconds, right? So the JVM does quite a bit of work. The ahead of time compiled mode doesn't do almost any work. There are some spikes where the actual work has to happen, but it's not that much. The ahead of time compiled mode uses something like 30 megabytes of RAM to serve those few requests. And the JIT mode uses a little bit more, quite a bit more actually here, right? And this is even the good thing. So this is the Micronaut example, which is quite efficient anyway. The support for native images in the ecosystem is quite broad, actually. There are a number of frameworks that position themselves as suitable for microservices that support GraalVM native images. That includes Helidon. If you would like something that is micro profile based, there is Micronaut, for which we had an excellent presentation before. There is also work to enable using native images as a deployment platform for Spring applications, the Spring Boot applications. And also, if you write command line applications, there's an excellent library called Pico CLI, which has integration with GraalVM native image. It can provide you and build your command line application as a native image, and it just works really, really great, right? So you have a choice.
Sorry for interrupting, Oleg.
Right.
There is a question. Well, someone is asking, why is that the throughput is higher in JIT mode? I would expect the native image is faster in any terms.
Right. That's a very good question. So the JIT has the best picture of what code is executed at runtime, right? It can also do speculative optimizations that are particularly suited for the given workload, right? The ahead of time compilation first needs to be more conservative. So, for example, you cannot not compile some branches because at runtime there is no way to kind of go back, right? In a JIT, with a JIT, you can also see that, for example, in an if block, you can always compile just one branch because your profile says that we're always there. and just trap the execution where you're happen to happen in a different branch or based on the data types, right? And then if the trap actually hits, right? If your assumptions are incorrect about what data and what code needs to be executed in the JIT mode, you can always go back to the interpreter mode and recompile again. So that allows it to speculate quite a bit, and that allows it to run. So the ahead of time compiled mode cannot technically be faster than that, right? So it can get a little bit closer, and for that you can use the profile guided optimizations, right? Which is when you record the profile of your execution, right? And then similarly, like the JIT does, right? It first collects the profile, collects the data, what is actually has to run, and then it compiles with that profile in mind. So you can use that to increase the performance of the native image ahead of time compiled code. Plus, of course, there is the implementation details. So yeah, we would like to get, like, technically, we'd like to get the performance of the ahead of time compiled, profile guided optimized native images very close to the warmed up JIT performance. But this is the work in progress, right? Right. So let's come back to the slides. Let's come back to the presentation. Out of the frameworks that are there, I personally like very much the Micronaut. I like the Micronaut approach for that. As the name says, it's a application framework that is typically, it's actually suitable for any applications, right? But it's also really, really good for small applications like microservices. And it provides you with anything that the normal framework will do: dependency injection and configuration and introspection and everything, integrations with a ton of metrics and ton of libraries and everything. But what it also does, it gives you the pre-computation of some important metadata and configuration. For example, the beans that you're gonna use can be introspected and pre-computed. The context can be pre-computed at the compile time. Micronaut uses the annotation processor for this, and so it's completely separate and happens before you actually output the bytecode for your application, which also suits native image very, very well. So I would recommend you to look at Micronaut application. I would like to show a quick demo, right? I will not do like a lot here, right? But I want you to get a feel of how the native image can be used here. So I have a small application here, right? It's a Micronaut application, right? You can see the tree. There is a bunch of files. It's all precompiled here, which could have cleaned it, right? Where's source, right? Reports, libs, maven clean. Wait, what's happening? Gradle clean. Doesn't matter. Let's go just look at the source, right? It's very simple. Source, main, Java, primes, web, primes. So application that looks like any normal application, right? It's main method and everything. And then we will compute the prime numbers. We'll compute the prime numbers. And this is just the controller. You can see that we're using annotations to identify the components. And we just say, like, let's map some URLs, and we will query that URL, and then we will generate two random numbers, and we will generate the prime sequence between those numbers. And the prime sequence is very simple code here. So we will stream the numbers between those two, and then filter everything that is prime and then collect that, right? Not the most sophisticated implementation, but it actually does some work. So it's a good example for that. How do I build native image? I can execute the native image utility, and you can see I have it on my path, native image -- version. Or I can run the Micronaut's Grail plugin for that simplifies this. So if I do what is build Grail, if I look at the build Grail, you can configure your native image plugin like here. I will remove all the options, and then you just do, what do you do? You do Grail, and then you do native image. And people say this process takes a lot of time, and this is horrible. And don't believe them. Don't believe them. If you're watching this now, you would see that actually it's not that horrible, right? So what needs to happen is that the native image utility need to analyze your whole application. That means those two classes that we actually saw, the whole Micronaut application and dependencies, all the dependencies that has, for example, dependency on Netty or dependency or any other or JDK standard library and everything else. So all that Java code needs to be analyzed together, figure out what will be used and what won't be used in the application. Everything that is not used will be thrown away, and only the rest will be compiled for our application here. So you can see it created the class list and started doing the initialization. It figured the type flow and created the objects. It ran the analysis. It built the universe of the objects that will ever be in the application. It uses some heap here. So it uses like something 5-6 gigabytes for the small application. It can grow a little bit more with the application being larger. So it's better to use like a sufficiently powerful machine, but well, build in the cloud. You can build in the cloud, and it's just fairly nice, right? So I feel that now this application build time could finish anytime, and that's not that bad. So it should take like a few minutes here, and we are on the second. Maybe you don't want to do this all the time while you're developing your application. The good thing is you don't have to. You can run your application in JIT mode. You can develop it until you're satisfied with the functionality, and then you can build the native image once. And then you satisfy, and you're actually, for your final consumption, you probably want your CI build your final native images anyway. And the workflow there is fairly simple. What you want to do, you want to run your application and your tests. While you run your tests, you want to generate the configuration using Java, the Java agent for the reflection and every other feature that needs to be configured. Then you use that to build the native image. You can build the instrumented native image that will be able to output the profile for you for profile guided optimizations. And then you build the final image using the configuration and the profile to build the optimized image for your particular workloads. Right, so we build it in 2 minutes. What do we have now here? We have written the native image in here. We can run it. You can see it runs really fast. I can show you that it runs, right? With this bench 8080 primes random 100, right? We see some numbers which are primes, and they just happen to be within some bounds that are randomly generated. The lower bound, upper bound, we have the top upper bound for the sequence at 100, so they're never larger than 100. If we have a larger number here, you can see that there are more numbers there. Very cool. Very cool. Can we do 10? Can we do like 2? Cool. Bound must be positive. It generated something there that is not positive. See, it's fully functional application. Right. So enough of this nonsense, right? What we want to do, this is the exception that was generated when we hit the application exception. Didn't want to do that, but since we had that, we created that. Right. So now let's analyze what this application looks like. If we do the LD, which is the which will list what our application actually, what our binary depends on, what it's linked against. Sorry, you can see that there is no JVM. It's just linked against the operating system libraries. So this means you can put this application in a very small Docker container that doesn't depend on that, and you can run it. If you look, so my a small example of that, could be the Docker file like this, right? You can use a random slim Linux that you would like to use. You can copy this application into that, and you can specify the entry point. So this is the slim thing. I can run it as a Docker image, right? Docker images. Don't remember what was the name. Prime swap slim, right? So I can do the dive. Dive is the utility to analyze the Docker images, and we'll do prime swap slim, right? So this is actually pretty cool, right? So our image is 200 megabytes and contains of two layers. One is the from, and the other is our application here, which adds what is it that? It adds the it adds just our file here, right? This app wasn't here before, right? So you can see that the image efficiency score is 100%, right? So you cannot get much more efficient than that. It's just the from and one layer of application. It also doesn't include anything else besides the base image and your application. So it's supposed to be, I think if you are a security professional, that should be a sign that this could be a very secure thing, right? You can go even further. So for example, if you build, you can configure native image to build the libraries statically into your image, except the libc, and then you can build a Docker file based, say, on the distroless Docker images, which would not even contain the operating system, just the smallest possible collection of libraries to run your statically built, your dynamically linked executable here. Sorry, right? So we can see if I do the prime swap here, prime swap, and this was distroless, right? It's even smaller. This one is what, like less than 100 megabytes in size, 94 megabytes total size of the image, and you can still run it very efficiently. Can I run it? Yeah. So let me run this. I will not run the PGO. I will run the distroless, right? For example, I will run the distroless in the Docker. I will constrain the memory and the swap, and I will give it one CPU, and I can run it. And you can see that it still runs really, really fast, even in such a constrained environment. And you can see that I still can access my application here, and it works the same way, reasonably fast here, right? So this is my application here running in a constrained environment. Let me bench 8080. I'm running cAdvisor on this port as well. And let me just show you Docker containers. I just want to show the stats for this particular container. The stats for this particular container, right? Let's go with the normal thing. This is our goofy Feynman, right? This is our container here. You can see that it doesn't use a lot of CPU, but the most important thing is the memory usage here, right? It uses 30 megabytes to have our microservice that computes some prime numbers. And that is very cool because that is not the memory consumption of a Java application that you normally see. Right. So you can always, you can build statically linked images as well, linking in muscle C. There are all cool tricks that you can do. So, but the most important things to remember here, if you have troubles, or if someone says that GraalVM doesn't work with reflection, just hit them with use the Java agent argument, and it works beautifully. Or use one of the frameworks that actually supporting native image and provides the configuration for that for you. And if you want to peak throughput, improve the peak throughput, and this is something that we had the previous question about, right? You can enable, and both of those are the GraalVM Enterprise Edition features. So you can enable the G1 GC garbage collection for the native image, improving the latency because then it doesn't include a longer GC pauses, right? And you can also use the PGO to improve the peak performance. And you need to build one auxiliary image to generate the profile, but then you probably do that in the CI anyway, right? And of course you can spice up with polyglot, but I will not go through the polyglot here because we don't have the time, and because it's mostly because we don't have the time, right? Oh no, right. So what GraalVM can do for you, if you just want to use your Java applications, right? If you run your Java applications normally, just use the GraalVM, the no-brainer. It probably will be faster. You can use it. You can save energy, save on the cloud compute costs, and you should try it at least, right? And if you specifically want the startup memory constrained runtime environments, you should keep GraalVM native image in mind. And for the new projects, it works really, really well because you can pick one of the libraries that are working really great. And you can build it, package in the small Docker containers without anything else, improving the security of those, improving the startup speed of those, improving the resource consumption of those, and deploy it to the cloud and enjoy the performance benefits of those for the cloud setting, right? And you might have a use case for polyglot, but there is definitely at least a full hour session about that later. Right? If you want support, if you want even better performance, you might want to look at the Oracle Enterprise Edition, Oracle GraalVM Enterprise Edition, which comes with even better compiler and the some other features. It's equivalent in a sense that it can run the same applications, and the same application can be run both on the GraalVM Community Edition and the Enterprise. But if you want support and additional performance bits, the absolutely best performance, then probably GraalVM Enterprise is what you're looking for. And of course, you don't have to, and you can just use GraalVM Community Edition that you can get from GitHub. It's under active development, so you should join the project. Please take a look at the docs. Please go, if you find anything that you would like to get improved, please create an issue on GraalVM, join the Slack workspace where you can talk to the team. And please join the community. I think it's going to be great.